So now we've started to dig deeper into identifying all of these symmetry operations that are contained within a given structure. And this is really important that we're able to identify and find these on an existing structure. We need to get very familiar with these operations, but it's an awful lot of work to compile a complete or near complete list of these symmetry operations. And so here we have these three structures drawn, right? We have our cyclobutane, we have our tetrachloroplatinate, and we have this trans-cyano-iron carbonyl, right? That's an awful mouthful just to get through on that one there. And if we were going to compile a list of all the operations as we did in our previous video, what we would see is that these compounds all contain the identity. They contain two C4 axes, or C4 operations, a C2, two C2 primes, two C2 double primes, a horizontal mirror plane, two vertical mirror planes, two dihedral mirror planes. It contains an inversion center and two unique improper rotations, these S4s. And so we said that if you count up all of these operations, these have an order of 16. And again, order just means the total number of symmetry operations for a given compound. But now that we have all these listed out, and we can look at these three structures and see that they all contain these same sets of symmetry operations, wouldn't it be nice if we could refer to them as a group, right? We can say these types of compounds all contain the same symmetry operations. So as far as symmetry goes, we can treat them in a similar fashion, right? And so it would be nice if we could group these up. Right? And this is the essence of group theory, is that we can group things based upon their symmetry elements. And sometimes it might be hard to see how these things relate. So this is an example where we've kind of dug deep into this. We've been able to see these different symmetry operations, but let's imagine something slightly different. So let's compare, staggered ethane. So if we go back to our organic chemistry background, right, we go back to our conformational analysis, we know that there is a staggered and an eclipsing conformation for ethane. And let's compare this to a chair structure for cyclohexane. Now these look very different, right? At least on paper, they look very different. And so if we imagine that these are all hydrogens along here, I always like doing this because I get a kind of nice cadence for my hydrogens as I go. And so these structures look very different, but as it turns out, if we were going to go through and try to list all their symmetry elements and symmetry operations, we can actually find that they are the same, right? They have the same sets of symmetry operations. So just like everything, they contain the identity. Their principal rotation axis is a C3 axis. They actually have three different C2 axes in each one of these structures. There are three vertical mirror planes. There is an inversion center. And there's actually two different improper rotations that we can list here. And so there's two of these S6 rotations. So we know that where we have the vocabulary, at least, to go through and find each one of these operations. And I'm going to challenge you between now and our next class to look at these structures, a chair of cyclohexane and our staggered conformation of ethane, and try to find each one of these symmetry operations, right? This is, again, a hard task here, but we want to be able to identify where these are, because what's happening now is we're going to be getting these lists of symmetry operations, and you're going to need to find these operations on a given structure, right? So now that you have the list, you need to be able to work backwards as well. So there has to be some way that we can group these together, right? As I alluded to on our first kind of set of examples, and now with these two molecules, we want to form a group, right? We want to say all these items have the same types of symmetry operations. So how do we group these? What are these labels that we are going to be using? So for this group, we're going to talk about how we get this in a second. but these get the label D3D, right? This is what we call the point group for these two structures, right? For staggered ethane and for cyclohexane. If we're going to put a label to a group here for our first set of compounds, right, these are D4H. And these labels, they don't mean anything yet. We're going to talk about how we derive them in a second. But we would describe all these compounds as fitting into the point group D4H. And we would talk about these two compounds, staggered ethane and cyclohexane, as fitting into the point group D3D. So how do we determine a point group? Well, we actually have a nice flowchart for this. And so this is posted on Canvas. This flowchart is going to be your best friend through the beginning parts of group theory as you're getting more and more comfortable with assigning these point groups, right? So this is posted on Canvas. So let's go through some examples, and we're going to see how we can determine these point groups for different structures. And so again, this is meant to get us to a point group. The point group then tells us all of this symmetry when we look up on a table what the point group contains. You'll notice the first question on our flowchart here is this group is it a high or low symmetry point group? And so this requires some kind of extra knowledge to be able to spot and identify high and low symmetry point groups. So let's start by talking about low symmetry point groups. And so these are some special cases where we have very, very few symmetry operations. And so it's hard to fit them into that kind of traditional flow for our flowchart. There are versions out there that ask some more pointed questions to get to these, but it's a little bit easier to see some examples and try to understand that the low and high symmetry just means very low order to our point group or a very high order to our point group. So the lowest symmetry point group we can imagine is something that only contains the identity. And so if we think about kind of a classic example of a chiral molecule you might have seen back in organic chemistry, where if we have a hydrogen and we just kind of mix up all of our halogens here, try as we might, the only operation that we can find for this particular compound is the identity, right? There's no other rotational axes, there's no inversion center, there's no mirror planes that we can draw for this structure. And so this gets a special label, right? This is in the point group C1. And so this is a special low symmetry point group where the only operation is the identity. And we can think of the C1 label here as being, again, just that the C1 rotational axis is the only thing we can do for this structure, right? Another example of a low symmetry point group would be something where we maybe have one more symmetry element, right, or symmetry operation that we can perform, right? So for this particular alkene, there's the identity, but there's also a mirror plane. And because the principal rotation axis is a C1, I can point that in any direction. So by definition, this is going to be a sigma H. And it is in the plane of my drawing surface, is my mirror plane here, right? So all of these atoms are contained within the drawing surface. So if I reflect, they end up not moving. And so this is another low symmetry point group, right? And this gets the point group label CS. And we can think of that S as being sigma for a mirror plane, right, or a reflection. And so molecules that are in the CS point group only contain the identity and a reflection. Okay, our last case is if we look at something that is a functionalized ethane, right? So a molecule that, again, should look kind of familiar to us. So we have the same kind of staggered conformation that we were looking at before. And this molecule doesn't contain a reflection. It doesn't contain any rotational axes, right? It contains the identity. And in this case, it also has an inversion, right? These are the only operations that are present in this structure. And the inversion, again, might be harder to see, right? If you need to practice, take some time and see if you can practice identifying this inversion here. This is in the point group CS. I. Again, I for inversion. And these are the only three low symmetry point groups, right? These are special cases with very, very few symmetry operations available to them. So let's look at our high symmetry point groups, right? So again, that first part of the flowchart is it a low or high symmetry point group? So here are our three low symmetry cases. Let's look at our high symmetry cases. So believe it or not, methane falls into a high symmetry point group. Right? There's a large number of operations that can occur here. And so for this tetrahedral kind of shape that's a pure tetrahedron, meaning all the substituents are the same, this gets the point group TD. Right? And you could think of this as tetrahedral, and it actually has a dihedral mirror plane, right? So that's where the D comes from. And if we were going to list out or try to list out all of our symmetry operations here, we have an E, we have 8 different C3s, 3 C2s, 6 S4s, and 6 sigma Vs, right? So the order here is 24. So this is a high symmetry point group, because there's lots of different operations, symmetry operations that we can perform on this structure. Another high symmetry point group is one that we've drawn quite a number of times this term, right? And that is an octahedral complex, right? So SF6 would be a good example of a high symmetry point group. This gets the label OH. Right? O for octahedral and H because there's a horizontal mirror plane. And so I'm not going to list them out because you can look up a table for this, but the order for an octahedral point group is 48. Right? So there are 48 different symmetry operations that we can perform on an octahedral compound. Now the last one, if you're looking around on Otterbein, you can look up these types of structures, and it is our last kind of special point group that is high symmetry. I won't give you one of these examples because I can't even draw them, so why would I give you something that is really difficult and challenging to draw? And this is an icosahedral structure. These have an order of 120. Right, they're not too many different symmetry operations. There's lots of redundant ones in there, but there's just a ridiculous number of transformations that occur for icosahedral geometries. Right, so these are our high symmetry point groups. Right, so these I'll label as our high symmetry point groups. I'm going to abbreviate point group as PG. And so we now have our low symmetry and our high symmetry point groups. There's one more special case to discuss, and this is the point groups that contain an infinite rotational axis, right? So something we would call a C infinity. And so this might look like hydrogen cyanide, right? So if we draw out this Lewis structure, these are linear molecules. Right, so these are linear molecules. And we can see that if we rotate about this axis, right, this is that C infinity rotational axis because we can rotate it in just tiny increments and it's indistinguishable from where we began. So if we were going to look at this structure, we would see that it contains the identity, as all things do. It would contain this infinite rotational axis, and it would also contain an infinite number of vertical mirror planes. And so these are all of the symmetry operations that we have available to us. And this earns the point group label C infinity V. Right, C infinity V. Now you could imagine another linear set of molecules, something like acetylene, which also has this infinite rotational axis, C infinity. But what makes this molecule different is that it also contains C2 axes, right? And so there's actually an infinite number of these C2 axes that we can rotate our molecule around. So for something like acetylene, this is a different point group, right? If we're going to gather up all of our symmetry operations, it contains the identity, it contains our C infinity axis, it contains an infinite number of C2s, it actually contains an inversion center, it contains also an infinite number of our S infinity, right? So it's the same kind of deal. If we have our tiny Cn rotation and then a reflection, right? That is our infinite axis. We actually have an infinite improper axis. Isn't that great and fantastic? We also have an infinite number of our vertical mirror planes. And so this point group gets the label D infinity H. All right, so D infinity H. And I believe, I left off on this list that there's also a sigma H. Sorry, sigma H is in there. And that cuts this molecule essentially in half. And so this gets the label D infinity H. And so what we can start to see when we're digging into this is that we first need to identify that principal rotation axis, but then there's a special feature that we tend to look for, right? What we're looking for is this perpendicular C2. So you might recall our last class activity where this was one of the checkboxes you were looking for, right? What is your principal rotation axis? And then, does it contain a perpendicular C2? So from here is where we can start to group up all of our new types of these point groups. So now we continue on in that flow chart. And the next question, right, that we run into is there a C2 perpendicular to Cn? And we can read this like a question, right? Yes or no, right? If there are, that puts us into the D point groups, right? So if yes, then we are into these point groups that all have a capital D for their label, right? And so within these groups now, we are looking at our principal rotations, and then it comes down to whether they have particular mirror planes involved. So let's get some examples for these D point groups as we move down the flow chart. So let's say that we do have this perpendicular C2 that puts us in these D groups. The next question on our flowchart is there a horizontal mirror plane? So let's look at a molecule like BF3. So this is a trigonal planar structure. We can see that it has a C3 rotational axis, right, that is coming directly out of our drawing surface. So this is our principal rotation axis is a C3. And we can see that we also have perpendicular C2s that go along my BF bonding axis. So these are these C2 rotations. So this puts me in the D point group, right? I currently have a C3 rotation and a perpendicular C2. So my next question is there a sigma H? And in fact there is, right? In the drawing surface of this molecule, there is a mirror plane, and this is a horizontal mirror plane because it is orthogonal to my principal rotation axis. So again, you need to practice a lot of these symmetry operations so that you get used to seeing them. So when I say something like, oh yeah, and this is a sigma H, you can identify that quickly, right? So we can get to this. So following our flowchart, we are now done, right? We would see that BF3 is a molecule that falls into the D3H point group. This 3 comes from our principal rotation axis. Right? Similarly, let's imagine that we had a molecule that did not have a horizontal mirror plane. So let's say we looked at something like allene. A friend of mine in grad school, my benchmate, worked on allene structures quite a bit. And so I've seen these in quite a number of research talks, but maybe you haven't in a while. These have a very interesting chemical structure. Allenes can actually be chiral, despite not having a single carbon with 4 different substituents. So these are kind of good gotcha kind of stereochem questions from back in organic chemistry. But here what we can see is that there is, in fact, a principal rotation axis that's a C2. And these can be kind of tricky to draw for this particular structure, but we can do at least the easy one first, right? So we have a C2 that's directly along the side. And there's an orthogonal C2 that is kind of going through the molecule. It's not exactly on our Z plane or our Z axis here, but we do have a C2 where our hydrogens can rotate and they actually switch, right? So I'm going to write that this is off axis. I'd advise you to look up the structure of allene on Otterbein so you can see this C2 rotation. It's a little bit tricky to identify. But now, again, we have our principal rotation axis, that's a C2. We also have a perpendicular C2 axis. So this puts us in our D point groups. Here I can see that I do not have a horizontal mirror plane. So if we look at this blue C2 axis, right, my horizontal mirror plane would be kind of like this. And because of the dashes and wedges, I do not actually have that horizontal mirror plane for this structure. So now I go down further on the flow chart, right, and it says, does it have a dihedral mirror plane, right, meaning does it have a different mirror plane that exists that is not a horizontal mirror plane? And if we're looking at this structure, it actually does, right? It's this plane that contains all of my carbons and 2 of the hydrogens is one of my vertical mirror planes. There's actually another one that is orthogonal to this particular mirror plane. And so now if we go through, so this is actually, sorry, I shouldn't have written a V. This is a dihedral mirror plane because it goes between these 2 hydrogens over on the side. So sorry, my drawing's getting a little messy here, but because it goes between those 2 hydrogens and it doesn't contain all of the atoms, we would call this a dihedral mirror plane. So now this final question, does it contain this dihedral mirror plane? Yes. So now we are in the realm where these would be D, in this case, D2, D is our point group. And again, this is just using that flow chart, right? Step 1, the highest rotational axis is a C2. Step 2, it contains a perpendicular C2. So we're in our D point groups. It does not have a horizontal mirror plane, but it does have a dihedral mirror plane. So the last case would be kind of our pure rotational case, if we're going to try to give an example for this. And so we can actually use a metal complex. So it's going to be a complex that the local geometry is octahedral. They are bidentate ligands on this molecule. And what I'm going to do is I'm going to abbreviate that kind of bidentate structure just by linking them like this. This molecule, well, it's very hard to see. It might be a little bit easier if I do my dashes and my wedges here. Actually contains a C3 rotational axis that is kind of sticking out of the surface, right? So kind of sticking out of the plane is our C3 axis. And what we can see here is that it does not contain any mirror planes. It does not contain a sigma H. It does not contain a sigma D. And so because of that, this is what we would call a pure rotational point group. If I can spell pure rotational point group. And so this doesn't have any of those mirror planes, and so we would just call this a D3. These kind of structures are, again, more rare. We'll see them sometimes with our bidentate complexes when we look at bidentate ligands, but it just takes some practice to see. Again, now that we have these labels for point groups, I'm going to recommend yet again that you go to Otterbein and you look at some of these symmetry transformations so you can actually visualize them a little bit better, right? Because you need practice, you need to be comfortable with identifying these point groups. Okay, so let's take a couple steps back, right? So let's imagine that we have molecules that do not have a perpendicular C2. Right, so if we go back to that point in the flow chart where we say, do we have a C2 that is perpendicular to our Cn? Right, if the answer is no, then now we are in our C point groups. Right, now we are in our C point groups. So we're going to be looking at some examples, right, that contain these different, that fall within the C point group. So all of these molecules fall within our C set of point groups. Wow, that's kind of hard to say. Meaning they have a principal rotation, but they do not have a perpendicular C2 axis. So if we're going to go through and identify kind of our principal rotation, This one is sticking straight out of the plane of the drawing surface, right? So this is a C2 axis where we can spin and we end up switching places between our chlorides and our fluorides and our hydrogens. Ammonia has a C3 axis that is currently in the plane of the paper of my drawing surface that allows me to exchange the location of these 3 different hydrogens. Similarly, for this alkene, there's a C2 axis that's pointed straight out of the page that allows us to swap the places of the chlorides and the hydrogens and the carbons. And so what we can see here is that these have these principal rotational axes. These are not in our low or high symmetry point group cases because they do contain a higher order CN axis. And so now we have to figure out what kinds of mirror planes do we have to work with here. So in our first example, right, there are no mirror planes here, right? There's nothing that we can do or no mirror planes that we can draw that switch the location of our substituents. And so again, this is one of those pure rotational point groups. So there's no sigma H, there's no sigma V, and there's no improper rotational axis that we can draw out here. And so what we have is a C2 is just the name of this point group. Again, this is one of those pure rotational groups. Pure rotational groups meaning the only symmetry operations that it contains are rotations. Right? It's not necessarily in our low symmetry point group, but the only thing it can do is rotate. In the case of ammonia, we actually do have some mirror planes, right? So we do not have a horizontal mirror plane, but we do have 3 different vertical mirror planes, right? And so these are mirror planes that contain the nitrogen and a single hydrogen. And so if we're following along on our flow chart, that means that this particular structure, right, for ammonia would be a C3V point group, right? So these are things that have this principal rotational axis. They do not have a perpendicular C2. They do not have a horizontal mirror plane, but they do, in fact, have vertical mirror planes. So our last example that we're going to be looking at here has the C2 rotational axis. It has no perpendicular C2s, but it does have a sigma H, right? And when it has this sigma H, we get off our flowchart early, and so we would call this a C2V point group, right? And this is all just examples that come from using the flowchart. So be sure to practice a lot with that flowchart and see if you can identify the point groups. So in our last class, we had this big chart that kind of walked you through this process without knowing you were walking through this process. Now what I want you to do, in addition to completing that chart, is decide on the point group for each one of those molecules. Each structure, assign it a point group using the flowchart. Write it in below the table that you currently have, right? So I get to add an extra line on that table. That is the point groups for each one of those particular compounds. And see what you can come up with. See if you can identify each one of those point groups along the way to share with your group.